In this lesson, we will find complex zeros of a polynomial and look at the fundamental theorem of algebra as well as the complex factorization theorem. A complex number is a number of the form a plus bi, where a and b are real numbers and I is the imaginary unit. Recall from previous math classes, I is equal to the square root of -1 and I squared equals -1. Some examples of complex numbers are 2 plus 6i, here a is equal to 2 and b is equal to 6. -3 is a complex number. You can think of b as being equal to 0 here. I is also a complex number. You can think of I as being equal to 0 plus -1 times I. Let's find all zeros of the polynomial f of x equals x cubed minus x squared plus 4x minus 4. I'll start by looking for rational zeros, and I will find the potential rational zeros of p over q. If we do that, we will have potential rational zeros of 1, plus or minus 1, plus or minus 2, and plus or minus 4. Let's start by testing x equals 1 as a rational zero. We'll divide x minus 1 into f of x. And here I'm looking for a remainder of 0. And it looks like that does happen. So x equals 1 is a 0. It also allows me to factor f of x into x minus 1 times x squared plus 4. And I can then solve for remaining zeros by setting x squared plus 4 equal to 0. I subtract 4 from each side and get x squared equals -4. So x will be equal to plus or minus the square root of -4, which is equal to plus or minus square root of 4 times square root of -1, or plus or minus 2i. So I have zeros of x equals 1, x equals -2i, and x equals positive 2i. Next, we will factor f of x over the real numbers, which we have already done. F of x over the real numbers is equal to x minus 1 times x squared plus 4. But we want to additionally factor f of x over the complex numbers, which takes a little more work. Remember that our zeros here were 1, 2i, and -2i. So I will use the zeros of 2i and -2i to further factor x squared plus 4. So we have f of x equals x minus 1. Remember, if 2i is a 0, then x minus 2i is a factor of f of x. And if -2i is a 0, then x minus a -2i is a factor. And just cleaning this up a little bit, I have the factored polynomial f of x equals x minus 1 times x minus 2i times x plus 2i. And this is factored over the complex numbers. The fundamental theorem of algebra. Suppose f is a polynomial function with complex number coefficients of degree n greater than or equal to 1, then f has at least one complex zero. Well, let's look at some examples. First of all, the function we've been working with, x cubed minus x squared plus 4x minus 4. This polynomial has degree of 3, so we should have at least one complex zero, and in fact we do have 3. Let's look at g of x equals x squared plus 4x plus 4. This polynomial factors into x plus 2 squared. So we will have a 0 of -2. So we have a degree of 2. We should have at least one 0 by the fundamental theorem of algebra, and we do. The complex factorization theorem tells us that suppose f is a polynomial function with complex number coefficients. If the degree of f is n and n is greater than or equal to 1, then f has exactly n complex zeros, counting multiplicities. Let's look at the same examples. Here, f of x equals x cubed minus x squared plus 4x minus 4. This has degree 3. So we should, according to this theorem, have 3 zeros, 3 complex zeros, and we do. 1, negative 2i, and 2i. G of x is equal to x squared plus 4x plus 4. And here we have degree 2, so we should have 2 complex zeros, but we only have 1. Well, something else is going on here. Remember, g of x is equal to x plus 2 squared. So this 0 of negative 2 has a multiplicity of 2. And what that means by the complex factorization theorem, we're counting negative 2 as being a 0 2 times because it has a multiplicity of 2. Try on your own to find all zeros of the polynomial f of x equals x cubed plus 2x squared plus x plus 2.